Troubleshooting IPv6 addressing. Every time I come to IPv6, I feel like I have to do a little more review. If not for you, for me. Because I feel like I keep relearning this protocol time and time again. Because I just... Okay, in the United States, you just don't use it unless you really want to. Like, I have a friend who works for a power company, and he's like, yeah, I rolled it out. I have an IPv6 internet connection here. And I was like, oh, did your company push you to do that? And he's like, no, I just wanted to. And so it's that kind of thing, you know? Now, I know. I talk to people around the world through CBT Nuggets, and I know many of you are running IPv6 everywhere. This may be review that you can just close your eyes through. So if you want to, feel free to fast forward. Here's the scoop on IPv6. Bajillion, zillion, million, crazy ton of addresses that it provides. You could go into all the crazy facts of, every grain of sand and molecule and human brain cell and everything else that you've heard that's off the chart. But at the end, it's a big old address. And we got to make this thing shorter. So a couple of the rules you can use to make it shorter is, number one, eliminate groups of consecutive zeros by using the double colon. And you'll see this done all the time, especially in a lot of the multicast addresses and things like that. You'll see like FFE0 colon colon, and then bam, you just get the rest of the address down to 1. So you can squeeze these really long addresses quite a bit with that. Rule number 2 to shorten these addresses is to drop off leading zeros. So things like this can go. Things like this can go to even further shorten these addresses. But at the end of the day, they are significantly longer and harder to type and more prone to mistype as we start talking about troubleshooting than IPv4. IPv6 addresses still do subnetting. It just gets bigger. We've got essentially the network over here, the subnet that you subnet it down into, and then the host on that subnet that comprises that address. Now, we're talking about global addresses, which are the addresses that work on the new IPv6 internet. And right now, the RFC has said that these global addresses will have their high-level 3-bit set to 001. So essentially we're planning to encompass the entire world, the internet, in a single IPv6 address to start off with, or at least putting this restriction on all those addresses. And right now, if you look at the IPv6 internet, or the Internet 2 as some people call it, you'll see all the addresses currently start with 2001/16. Every single one of these I want to call them octets because that's what you would call them in IPv4, but when you go colon, things like that, colon, each one of these are 16 bits in length. So essentially it goes 16, 32, 48, 64, and as you go on. So that's really how you structure your subnet mask. So take a look at this. Global routing prefix is 48 bits or less. That's essentially the major network that's being defined, and then after that you have the subnet that will typically be it. Again, you can do all kinds of crazy stuff with your IPv6 addresses, but if you want to stick to standards, you want to work well on the internet, then you want to set your subnet that will be 64 minus n bits. So essentially, if you have a global prefix or what has been allocated to your company as a 48-bit prefix, then you've got 16 bits left for the subnet. So essentially, that would mean we've got, let's just say 1111, 111, 1111. That would be your global prefix, and then maybe we have a subnet of 2222, right, colon, and then the rest of it would represent the host. Now, the host itself is typically represented by the interface, because we're going to see in just a little bit that there's this method called EUI64 allowing the host to generate their own IP addresses, and they can do that by taking their MAC address, right, which is 48 bits, and splitting it right down the middle. So let's say they've got the MAC address AA1111. They squeeze in FFFE in the middle of that and then put the rest of their MAC address, so BB2222 at the end of that, right? To give themselves 64 bits that they can plug in as the interface ID, thus creating an automatically generated address. I don't want to talk too much about that right now because we're going to talk about that completely. But the subnets that are being assigned to providers are typically /32. So essentially the global prefix becomes /32. That's given to an ISP, right? Who then chops it up and gives it to their customer, and they've got now 32 bits to work with to subnet that out for their own likings and handing it to all of their individual customers. Now, when it comes to communication, we need to remember that broadcasts are gone as of IPv6. Everything has been replaced by a multicast. So that requires us to restructure a lot of our communication, like ARP. ARP was a broadcast message that helped us resolve IP address to MAC address, so they came up with a totally new neighbor discovery process that is ICMP based, and it's called neighbor solicitation. So let's just say this guy right here wants to be able to communicate with the PC over to the right hand side, right? This PC, let's just say, is 2001 DB8 6783 123, that's the subnet that would go right there. Colon, let's just say 52, right? It's all zeros up to the last two hexadecimal digits, which is 52. What happens is that computer automatically joins the solicited node multicast group FF02 : 1 : F and then the last 6 digits of its MAC address. I know if you're like me and it's been a little while, you're probably like, say that again? How did that work? So remember the whole problem with ARP, right? If you've got a, I'll say, simple 5-port switch right here, and this guy just wants to talk to the other guy, he has to disturb all the computers attached to this, and it could be hundreds of computers in a larger network because he has to send an ARP broadcast. Well, they've improved the ARP process so much because this thing, when it realizes what its IP address is, and I'll talk in just a second about how these things get their addresses, it automatically joins a multicast group. FF02, this by the way is link local multicast addresses. It stays always on the link that it's on. : 1 : F, and then the last whatever digits of the IP address are in there. Now it automatically joins its MAC address, and I'll explain that a little bit later. Let me just give you the result. Is it's going to join FF02 : 1 : FF, and then it would be 00 : 0052. It would actually join that multicast group, right? And so on the switch, represented by this little bar, it would say, okay, port fast Ethernet 1/10 is joined to this multicast address. Now, when this guy goes to send an ARP, he knows the IP address he's trying to communicate with, right? He resolved it via DNS, or you typed in ping and the 2001 52 as the address, right? So when it sends an ARP message, it actually sends it to this multicast group because it knows, because of the rules of IPv6 and how it generates its addresses and handles neighbor solicitation, it knows somebody's going to be listening to that multicast address, so it goes into the switch and only bothers the port attached to that one device, right? So instead of it having to send a broadcast or a multicast that reaches all the nodes, right, it just comes in as this solicited ARP message that, and it's not called ARP anymore, I just said that goes directly to the device because that device joins the multicast group based on his IP address. It just, again, puts the last few digits of that address in there. So that's one of the improvements, along with many of the other ones. All of our broadcast-based communication has now all gone multicast. Instead of seeing like 224.0.0.x like we would in the IPv4 world, like .6 would be OSPF designated routers, .5 would be all OSP for router. Now it's all been replaced by this FF02::, and then the unique last digit based on what you're after. Now let's get a little more nitty-gritty. How do you get an IP address in IPv6? And I'm thinking about this from a couple of perspectives. One, let's just say we've got the router connecting off here to the internet. How do you assign that guy an IP address? And then what about the PCs on the network segment? How are they getting it? Well, there's a number of ways, and there's no right way to do it, but there's easier ways than others. The first and probably easiest way is stateless address auto configuration by using a router solicitation to the routers on the subnet. You probably saw on the last slide that one of the addresses that you could send out to was FF02, which actually reached all local routers on the subnet. So it would go out. That's called a router solicitation message. And when a client boots up, it can say, hey, router, hey, I need to know what network I'm on, because if the router tells it what network it's on, it can fill in the rest of the address. Remember, if it gets the first 64 bits of the network identifier, it can fill in the last 64 using that EUI 64 method. So we can go into our routers. Let me just bring a router up into the picture. First off, always remember to turn on IPv6 unicast routing. IPv4 routing or IP routing is on by default on every Cisco device. Not so much when it comes to IPv6 because not everybody uses it. So I'm going to go into interface fast Ethernet 00. I'll do IPv6 address. And we'll say 2001:1:1:1:1, right? /64. Nice, cheesy generic address that we can assign to it. And by the way, notice we can also say to our router, I want you to go get an address using auto configuration, at which point it goes to other routers on the segment saying, hey, what network am I on? And tries to fill in the gaps there. So I'm going to do a show IPv6 interface fast Ethernet 0/0. If I can type that. And you can see there's my address. There's my subnet. Based on that /64 mask that I put on there. Ooh, look at this. This is also it joining the multicast group. Remember that router solicited address? Wait a sec. Did I say? I think I just did that wrong. Yes. FF02. Did I say that? ::2 goes to all routers. That's the router solicitation message. But you can see that right here. It has joined essentially the all devices multicast address, which essentially replaces the broadcast, and it's joined the all routers multicast address right there. Now right below, it automatically joined this multicast group, which is the one that helps other hosts resolve its MAC address. Remember, this is the neighbor solicitation message when it's trying to ARP for this address. It's saying, well, this is FF02::1, FF, and then this is the last 6 digits right here of the MAC address with the 0 rule engaged because it removed the leading 3 zeros there, right? Is that making sense? Now notice up here, it also has a link local address. Now this happens for every IPv6 host. It will generate a link local address, which is FE80::, and then it puts its MAC address with that FFFE, that's the EUI64, jammed in the middle, right? So this is the MAC address, the 6 digits to the left with 0 shortening in there, and the 6 digits to the right with the 0 shortening in there, with FFFE put in the middle to make it a 64-bit address. It's also joined to the multicast group for that. Link local addresses is used for essentially local communication when you are talking routing protocols or other thing. Oh, pinging somebody on the Cisco Discovery Protocol, stuff that happens locally, right? That's all with that link local address. Second way that you can do it is stateful DHCP. So this is exactly like the DHCP of IPv4 world, right? We define a pool of addresses, add our exclusions on there, and the router will hand out the IP addresses to the segment. The benefit of having that is now you've got a record of it, right? You've got the binding table, and you can say, here's all the IP addresses, here's the MAC addresses, just like traditional IPv4. Now you can use what's called stateless DHCP, which allows the essentially auto configuration to happen. You know, it kind of gets its address by sending a solicitation message, then filling in the rest of it with EUI64. And then it says, okay, but I need the other DHCP options, like DNS servers. I like option 66 if you're an IP phone. Or wait, no, it's option 150. Well, actually, it's either 66 or 150 in the Cisco voice world to get the TFTP configuration for a Cisco voice over IP world. So again, there may be options that you want to hand out via DHCP that stateless auto configuration doesn't cover. That being said, before you throw auto configuration out the window, because when you first hear that, you're like, oh, well, if I have to configure DHCP anyway, I'm just going to do this. Why not just go old school? There are RFC standards that using stateless address auto configuration, the router can also hand out things like DNS servers, can hand out the default gateway. And as a matter of fact, it does that by default. When this guy auto configures, it will point to the router that gave it its router solicitation message, right? So there's more than meets the eye than just generating an address. It can do some base configurations as well. This is if you want to go beyond the basics. This one, DHCP relay agents, just like it was before, you can have centralized DHCP services, maybe on some kind of Windows server or Linux server. So this guy can receive those, relay them down to whatever server you specified. So what could go wrong with this IPv6 world? Well, plenty. First off, you got to make sure that you have unicast routing turned on, and that was the going into global configuration mode, IPv6 unicast routing, and make sure you have an IPv6 address assigned under the interface. The router does not generate those link local addresses until you assign some other IPv6 address to the interface. Now you can go in and manually assign a link local address if you want, and that enables it. But essentially, if I do no IPv6 address, right, and I go back and do a show IPv6 interface, it's going to say nothing there. Not even the link local, no multicast groups, nothing is happening until you manually go in there and give it something. So I'll do IPv6 address 2001:1:1:1, right? Throw that back on there, and now we've got the whole flex of it. Now, the whole flex of it, where do I get these things? So the whole shooting match. So here's the interface. Fast Ethernet 0/0 is up. You can see it generated that link local address. You get a lot from this show IPv6 interface, all the multicast groups. You can see that the hosts are using stateless auto configuration, so it's sending the neighbor discovery. That's what I was showing you on the previous slide. Neighbor discovery advertisements, so the host can get that if it's requested. So also make sure your interface is using a /64 prefix if you hope to have it do auto configuration, because auto configuration relies on that EUI64, which uses the other 64 bits to fill in the gap. It doesn't work if you use a subnet mask other than a /64. Router advertisements are suppressed. That could be something that goes wrong. Now, why would you do that? Well, maybe you're writing a T-shoot exam and you're like, maybe this would be one that catches people. Doing an IPv6, let's see, what would it be? Neighbor discovery. Remember I was saying neighbor discovery commands, previous slide. That's how it discovers the different things. And you could go in, if you were just mean, and type in suppress router advertisements. At that point, the hosts that are sitting there on that segment saying, hello, I'm trying to figure out which network I'm on. Router, would you help a brother out? Routers would be like, no, because somebody typed that suppress command in there. Maybe I'm trying to figure out why you do that in the real world. Maybe you've got 50 routers on the segment and you don't want them all responding at the same, I don't know. I'm coming up with things, maybe. So DHCP misconfiguration, that would be the same kind of thing as IPv4, where you mismatched the pool to the interface, or misconfigured the pool, or didn't exclude the right addresses from the beginning. So show commands that I have down here are virtually the same as IPv4. This one's handy because there are so few. Well, you can have many, but most people have very few IPv6 commands in the running config. So just doing a show run include IPv6 will give you a quick flush of here's what you got going on, and expose things like this very quickly that could be thrown in there to throw you off. That's the basics of troubleshooting IPv6 addressing. I hope this has been informative for you, and I'd like to thank you for viewing.